Section. Introduction. Every day, people worldwide generate a vast array of videos, including live streams, video game streams, short clips, movies, sports broadcasts, and advertisements. These videos, which convey information through text, visuals, and audio, present a rich and diverse medium. If we can develop methods to learn from these different modalities, we can create more advanced machines capable of analyzing unedited real-world videos, going beyond the limitations of carefully selected datasets. However, the complexity of these videos presents many challenges, especially when dealing with long-duration videos. Understanding videos that last over an hour requires sophisticated methods that can analyze sequences of images and audio across multiple episodes. This task becomes even more complex when we need to extract information from various sources, like identifying speakers, recognizing characters, and maintaining narrative coherence. Answering questions based on video evidence also requires a deep understanding of the content, context, and subtitles. Live streaming and gaming videos present their own unique challenges, as they require real-time processing of dynamic environments, semantic understanding, and long-term strategy planning. While recent advances have been made with large pre-trained video models and video language models, these models are typically trained on short clips or predefined action classes. As a result, they may not provide a detailed understanding of complex real-world videos. To better understand the videos we encounter daily, we need methods that can handle these complex challenges. This involves not just identifying who is in the scene and what they're doing, but also understanding when and how they're acting, and recognizing subtle visual cues across different scenes. In this work, we aim to address these challenges and explore methods that can be applied directly to real-world video understanding. Our approach involves breaking down extended video content into coherent narratives and then using these narratives for video analysis. Recent advances in large multimodal models, LMMs, such as GPT-4V, ision, have shown significant progress in processing both input images and text for multimodal understanding. This has led to interest in applying LMMs to the video domain. In this work, we present Mvid, a system that combines specialized tools with GPT-4V for video understanding. Mvid works by performing multimodal pre-processing on an input video, including scene detection and automatic speech recognition, ASR, to gather important information. The video is then split into multiple clips based on the scene detection algorithm. GPT-4V is then used to take the clip-level video frames as input and generate a detailed description for each video clip. Finally, GPT-4 is used to generate a coherent script for the full video, based on the clip-level video descriptions, ASR, and any available video metadata. Our experimental results show that Mvid is effective in different challenging scenarios. It can understand hour-long videos through multiple modalities and locate specific events with accurate timestamps. Mvid also shows promising results in interactive environments, such as predicting the next steps in a video game or interacting with a graphical user interface, GUI. Previous work in video understanding has focused on building video foundation models, which have been successful at analyzing short video clips. However, these models are typically pre-trained with vision modality only and may require specific adjustments for multimodal downstream tasks. Recent studies have made significant improvements in multimodal representation learning for video and language understanding. These advancements have been particularly evident in popular downstream tasks such as video question answering, text video retrieval, and video captioning. However, these methods are usually trained on short video clips, which can pose challenges when trying to understand longer video sequences. Inspired by the success of large language models, LLMs, recent studies have suggested using a frozen LLM combined with an image encoder and a few learnable modules for video understanding tasks. While these models show promise, they may fall short when dealing with videos of extended duration. Our work aims to address this gap by exploring methods that can be directly applied to understanding long videos in real-world situations. Recently, researchers have been exploring the LangChain system paradigm, which integrates expert tools with existing LLMs to create new functionalities. For example, Vlog uses Blip2 and Grit as dense image captioners, Whisper as an ASR translator, and ChatGPT as a reasoner. By transcribing a given video to textual descriptions, it enables ChatGPT for video question answering tasks. Inspired by the effectiveness of these tool-using approaches, we explore integration with GPT-4V for video understanding. Section Summary. Videos are a versatile medium for conveying information, but understanding long videos poses challenges in analyzing sequences of images and audio across multiple episodes. Existing models trained on short clips or predefined action classes may fall short in comprehending intricate real-world videos. To address this, we propose MVID, a system that integrates specialized tools with GPT-4V to break down extended video content into coherent narratives and generate detailed descriptions for each video clip. Experimental results demonstrate MVID's effectiveness in comprehending hour-long videos, localizing events, and predicting next steps in interactive environments. Section: Preliminary Study with GPT-4V, ision. We've been exploring the capabilities of GPT-4V, a model that can understand a variety of inputs, including text, questions, and even visual cues like images or short video clips. This ability to interpret visual inputs and generate relevant text opens up a world of possibilities. For instance, by feeding GPT-4V a sequence of frames, it can understand time-based relationships and interactions, which helps it identify and interpret dynamic visual content. We've developed a system called Mvid, which takes a video file and outputs a script describing the video's content. This script allows language models to understand the video in various ways. Mvid has four main parts: multimodal preprocessing, external knowledge collection, clip-level video description generation, and script generation. In the multimodal preprocessing stage, we start with a video file and use a tool called ision to transcribe the video's audio. We then divide the video into short clips, each containing 10 frames. To improve the quality of this process, we use scene detection tools like ision detect to identify important scene boundaries. In the external knowledge collection stage, we gather additional information to feed into GPT-4V. This could include metadata, the video's title, an abstract, and even photos of characters in the video. In our tests, we collected the metadata, title, and abstract from YouTube. During the clip-level video description generation stage, we use GPT-4V to generate descriptions for each video clip. By feeding the video frames and associated text prompt into the model, GPT-4V generates detailed descriptions that capture the visual elements, actions, and events in the frames. We've also found that including photos of characters along with their names in the input to GPT-4V can improve the quality of the video descriptions, especially when it comes to identifying characters. In the final stage, script generation, we use GPT-4 to combine the descriptions for each video clip into a coherent script. This script serves as a comprehensive description of the entire video and can be used by GPT-4 for a variety of video understanding tasks. We've also tested Mvid with streaming video inputs. In this scenario, our system acts as an agent in a dynamic environment where streaming video frames are the primary input. The agent continually receives and processes these frames, making decisions and generating responses. By continually analyzing the streaming video frames, Mvid can transform raw visual data into meaningful insights, which could be useful for applications like video gameplay, embodied agents, and GUI navigation. We've conducted several experiments to test Mvid's capabilities. We used the Azure Cognitive Services APIs to access the ision tool and ision detect for scene detection. Our tests showed that Mvid can handle a variety of tasks, including answering questions based on the video content, integrating visual and auditory cues to provide accurate responses, processing lengthy videos, analyzing multiple lengthy videos, identifying characters, improving the quality of automatic speech recognition, generating audio descriptions, refining its own output, and accurately describing fast-changing short videos. In summary, our experiments have shown that Mvid is a versatile tool that can process a wide range of video content and generate meaningful and contextually relevant descriptions. Section Summary. Recent studies have shown that GPT-4V, a language model, can comprehend visual inputs like images and video clips, enabling a wide range of applications. Mvid, a system pipeline, utilizes GPT-4V to generate video descriptions by processing video frames and associated text prompts, allowing for tasks such as grounded question answering, multimodal reasoning, hour-long video comprehension, multi-video episodic analysis, character and speaker identification, audio description generation, self-refinement, and handling fast-changing short videos. Section: Applications to interactive environments. We're going to delve into the practical applications of Mvid, a tool we've developed that can interpret and interact with streaming video inputs. Firstly, let's consider its use in an interactive environment. Mvid acts as an agent, constantly receiving and processing video frames. For instance, we've used it with a video taken from a head-mounted camera, giving us a first-person view of someone's daily life at home. Mvid was able to understand the content of the video and assist with tasks such as locating items in the house and tracking the wearer's activities throughout the day. We've also tested Mvid with video games, specifically a Mario game. The agent received 3 video frames at a time and calculated the next move. It showed a good understanding of the game's dynamics and was able to make sensible decisions about how to play the game. In another scenario, Mvid was used to navigate a graphical user interface, GUI. The agent received screenshots from an iPhone and previous user actions, and was able to predict the next steps in the user's journey, such as clicking on the correct shopping apps, searching for items, and placing an order. We also conducted a study to explore the potential of Mvid for people who are blind or have low vision. We used it to generate audio descriptions, AD, for videos, providing important visual details through narration. We invited 9 participants to evaluate the effectiveness of these audio descriptions. 4 of the participants were either blind or had low vision, while the remaining 5 had normal vision. We used a selection of videos for the evaluation, some of which were suggested by the American Council of the Blind. Participants were shown 2 versions of each video, one with human-generated AD and one with Mvid-generated AD. Both versions were narrated using text-to-speech technology. Participants with visual impairments were asked to evaluate the videos based solely on the audio, while those with normal vision were asked to consider both the audio and visual elements. They were asked to rate various aspects of the videos on a scale of 0 to 10, with higher scores indicating more positive feedback. The results showed that Mvid-generated ads were rated close to human-generated ones in terms of effective delivery, informativeness, and voice and audio quality. However, the overall satisfaction with Mvid-generated ads was slightly lower than with human-generated ones. Some participants reported difficulties with overlapping audio and incorrect descriptions. Despite these issues, all participants agreed that Mvid-generated ads could provide a cost-effective and scalable solution for making videos accessible to the visually impaired community. Section Summary. In this section, the authors evaluate the performance of Mvid in various interactive environments. They demonstrate that Mvid can understand and assist users in practical tasks within a home environment, play video games effectively by understanding game dynamics, and navigate graphical user interfaces seamlessly. Additionally, they conduct a user study to assess the efficacy of Mvid in generating audio descriptions for people with visual impairments, showing that while there are some difficulties such as occasional overlaps and wrong descriptions, Mvid can provide a cost-effective and scalable solution for making videos accessible to the visually impaired community. Section. Results on the group with normal vision. We conducted a study on individuals with normal vision using the same set of videos that we used for visually impaired participants. Each of our 5 participants watched these videos, which had audio descriptions, AD, generated by our system, Mvid, embedded as subtitles and audio tracks. After viewing, they answered 6 questions listed in a table. We had 3 hypotheses for this study. 1. The AD generated by Mvid is accurate and doesn't overload the listener with information. The results showed that the participants rated the clarity and accuracy of the Mvid-generated AD at an average of 7.83 out of 10, with a standard deviation of 1.24. In comparison, human-curated AD was rated at an average of 8.9 out of 10, with a standard deviation of 0.74. When it came to conciseness, the Mvid-generated AD scored an average of 8.73 out of 10, with a standard deviation of 0.49. While the human-curated AD scored an average of 9.16 out of 10, with a standard deviation of 0.54. These results suggest that the Mvid-generated ads are almost as accurate and concise as human-curated ones. 2. The ads generated by Mvid are synchronized with the visual content and don't interfere with other dialogues, allowing listeners to follow the storyline. The participants rated the informativeness of the human-crafted AD and Mvid-generated AD at an average of 8.90 and 7.97 out of 10, respectively, with standard deviations of 0.90 and 1.54. In terms of timing and synchronization, the human-crafted AD and Mvid-generated AD scored an average of 8.59 and 8.53 out of 10, respectively, with standard deviations of 0.95 and 0.58. These results indicate that the Mvid-generated ads are almost as effective as human-crafted ones in terms of timing and synchronization. 3. The voice and audio quality of Mvid-generated ads are comparable to human-crafted ads. The participants rated the voice and audio quality of the Mvid-generated AD and human-crafted AD at an average of 8.30 and 8.93 out of 10, respectively, with standard deviations of 0.89 and 0.32. This suggests that the voice and audio quality of the Mvid-generated ads are almost as good as those of human-crafted ones. The feedback from the cited participants helped us validate the hypotheses of visually impaired individuals, which were based solely on audio cues. Although the overall satisfaction score for cited participants with Mvid-generated ads was slightly lower than that for human-generated ads, the difference was less than 1 point on average. The overall satisfaction score for blind participants was lower, which was expected because they only had access to the audio modality. We believe that the lower satisfaction score might be due to the lack of practice listening to auto-generated ads. Some participants also expressed preferences for certain voice pitches and the number of concurrent audio channels, which might have contributed to the lower satisfaction score. We also collected feedback from our visually impaired participants, who shared their personal experiences and insights about the ads generated by Mvid. They unanimously expressed a desire to continue using this AD generation service in the future, praising its high quality, detailed descriptions, wide applicability, and the independence it offers. However, not all feedback was positive. Some participants expressed skepticism about the subjective nature of the ads and the use of names instead of pronouns. Some also had difficulty dealing with overlapping or parallel audios. Despite these criticisms, even the participants who provided critical feedback rated the Mvid-generated ads closely to human-generated ads, suggesting that getting used to Mvid-generated ads might require some practice and acclimatization over time.